Hello, everybody. Sorry about that. Still figuring out Zoom a little bit. Um, my name is Brendan Zink, and today I will be presenting on groundwater pollutants of the Yucatan Peninsula. And so I wrote a paper looking at how sea level rise, urbanization, and saltwater intrusion will pose challenges for freshwater access in the future. So I wrote this water for my ENS 340 class, and I'm just basically looking at how water equity is going to change as the climate of the Yucatan Peninsula changes and what that means for people's ability to access water. So, to really get into this, you have to understand the landscape of the Yucatan Peninsula. There are no lakes or rivers, so the only source of fresh water is from the aquifer. And so I have a diagram of that right here. You have a freshwater zone and a saltwater zone, and then you have that separated by something that we call a halocline. And as the aquifer is the only source of fresh water in the area, it is very important that it does not get contaminated because then you can't provide for the people. So making sure that halocline stays kind of stagnant or not intruding into the fresh water is very important for providing water equity for everyone in the peninsula, especially as populations increase. So looking at haloclines, looking at how that's calculated is very complicated. I tried to look into some of the physics equations of it, but it was a bit too hard to condense down into something palatable for this class. What you need to know is that it depends on a lot of factors, including temperature of both waters, salinity, the sea level, hydraulic conductivity, which is how well the water can flow through the karst environment, through the rocks, the limestone, the flux of the aquifer, which is the pressure that the water pushes out, the fresh water pushes out onto the salt water, and the head of the aquifer, which looks at how high the water table is. And so just to give you a bit more information on them, I kind of have a diagram of sinkholes and their respective haloclines. Um, when you have sinkholes or cenotes closer to the coast on the Yucatan, their haloclines are a lot higher in altitude. For example, this one is only about 12 meters, whereas this one, which is further inland, is 30 meters below ground, which would be lower in altitude. But ultimately, the halocline is contingent on a lot of interactions, and we're going to look at how some human effects play a role on what might influence that halocline to rise. So, any rise of this halocline would lose precious groundwater. And ultimately, what we're seeing is there's a risk to this halocline rising that is exacerbated by climate change. Groundwater temperature is projected to increase just as the entire surface of the globe is increasing its temperature, and that is projected to elevate the halocline due to its interactions with the salt water and the fresh water. Additionally, human interactions also have a role on this interface. Right here we have a diagram of the Merida well fields and its interactions with the aquifer. So right here we have Japai 1, which is pumping up fresh water to supply the city and meet its water needs. It is thought that these wells, which are all kind of clustered, put a pressure on the water source upwards, which in turn pulls the halocline upwards with it. And that's a bit scary. If you eventually pull hard enough and that halocline reaches the freshwater wells, then you can't provide potable water to the city because it's brackish now. So that's just one way that human impacts have a role on the halocline. One other way is through our injection wells, as this is kind of, I guess, the opposite of the well field. By injecting the wastewater downwards into the unusable salt water, another bump in the halocline is created by putting all that mass into the system. You're putting pressures on the brackish water upwards and possibly losing some more of that fresh water in the process. So what this represents is kind of just an intrusion of contaminants at the bottom of the aquifer, which could pose a threat in the future to their water source. What ultimately is a much scarier thought is saltwater intrusion. And so saltwater intrusion is just pretty much the ocean slowly getting in underneath the halocline higher and higher and taking it over as the ocean maybe at one point. So this happens little by little, and the coast is particularly vulnerable. And so as the climate changes in the future, we know that sea level is expected to rise. I looked at a bunch of models, and they expect it to rise by about 1 meter in the next century. However, some other projections can put that as high as 2.5, just to give you some perspective. So what I found was a really nice study looking at Kanzanaru, and it projected how sea level rise will affect their freshwater aquifer. And so it had a bunch of projections, but just to kind of simplify those down, I have two right here that are probably the most important. Here, let me move me over here so you can see the title. So the models looked at how the flux of the water would change, the flux of the aquifer, the freshwater would change saltwater intrusion. So what we see here is as sea level rises, what we have here on the x-axis is sea level rise, and right here on the z-axis you have how many meters of intrusion would occur. So what we can see here is if the flux of the aquifer stays at 100% freshwater with this level of sea level, with this amount of sea level rise, then 300 meters of fresh water will be lost to saltwater intrusion. However, if that aquifer flux is decreased to 30% and sea level rise increases to 1 meter, then 1,000 meters of fresh water would be lost to saltwater. So ultimately what this is showing is that billions of gallons of fresh water are estimated to be lost due to saltwater intrusion, and that is not a great outlook for the Yucatan Peninsula, as they need that water, or as water is scarce, and losing billions of gallons to saltwater is not ideal for anyone. So beyond saltwater intrusion, which really hits the bottom of the aquifer, we also have urban impacts, which also can contaminate the freshwater source. So we know that there's an increasing population on the peninsula. So just taking us back to slide 2, where we had the wells and the injection sites, the higher population you have, the higher the demand and the load on the wells and injection sites are going to be. Wells are going to need to pump more water to provide for more human needs, and it's just really going to increase that rate at which the halocline is brought closer to the well, to the mouth of the wells. So that is one factor, but what we also have is that the urban landscape increases runoff and pollution and leads to contamination of the aquifer as well. As these natural landscapes were removed to install cities and concrete, which does not filter water, water ultimately runs off and picks up dangerous chemicals with it and contaminates the aquifer once it seeps into the ground. So this is a good example of this is septic tanks, which can introduce waste that we obviously don't want to be drinking into the groundwater. And so it's estimated that the upper 15 meters of the aquifer unfit to drink. Just to give you some perspective, that's about 1/3 of all of the water in the aquifer. And so right there you see that a lot of what could have been fresh water is not actually potable, and you wouldn't want to drink it. So what I'm trying to get at right here is that you have contamination at the top and the bottom of the aquifer. Human impacts have introduced pollution from the top due to their cities, and sea level rise and halocline rise, which is also factored by humans, is introducing saltwater from below. So while there is still fresh water in the area, it's in a Goldilocks zone of kind of in between contamination at the top and the bottom. So considering this risk of pollution, let's look at some solutions to this decreased access in the future. What ultimately needs to be done is a lot more research on wells and their interactions with the groundwater. The paper I read on Quintana Roo really said that studies need to be done on placing wells where their locations, where they should be placed, the altitude at which they should be placed, and the rate at which they pull or inject water. So doing more research on the fluid dynamics of where you can put wells, how close you can clump them together without affecting the halocline, and the speed at which they can pump up water. That's going to be very important to looking to provide for more people on the peninsula. However, another solution that I found was physical barriers that could be used to slow saltwater intrusion. And so the method I found kind of was the reciprocal of what we have from the Japai 1 well fields pulling up the water. Instead of pulling up the water and pulling the halocline with it, if you pump water downwards towards the halocline, you can kind of create a pressure that pushes back. And so this method pulls salt water up on the opposite side of the halocline, relieving the pressure on the halocline, pulling that back downwards, and then pumps fresh water down to push the halocline downwards as well. Not necessarily push, but just put that pressure of fluid dynamics upon that freshwater saltwater interface. So here's the model for that. This relies on an impervious bottom. So I'm not positive on its feasibility throughout the entire peninsula, but if you have locations where there is kind of rock bottom, then you could take injections wells, push the salt water down at the halocline, and put that force on it, and then pull salt water up and send it back out into the sea somewhere else, and just kind of create a new system of pressures and fluid dynamics in that area. And so that would help keep the water clean. So just to go back through this, what we have on the Yucatan Peninsula is a contamination of the aquifer. It's occurring, it will be occurring in the future, and there's not a lot we can do about that. At the top, that's from human impacts, which we can try to mitigate, but at the bottom, saltwater intrusion and halocline rise have a lot of factors, including just global climate change, which can't really be stopped. So ultimately, this isn't too serious of an issue currently, but looking far down the line, this is something that needs to be solved. The Yucatan Peninsula only uses 1.4% of fresh water, the rainwater each year, so it's not super pressing, but as you increase population and as you increase pollution and contamination as well, taking care of the aquifer needs to be a high priority. To solve this problem, more research needs to be done to understand the pumping dynamics, and additionally, perhaps considering a physical boundary to slow saltwater intrusion could be done. So there was my paper. If you guys have any questions, please let me know. My email is brendan.zink@center.edu. If you would like to read my paper, just ask and I can send it to you. I hope you guys liked this video and enjoyed learning about the Yucatan Peninsula. Here are my sources. They look a lot better on the paper as well, but what we have here is a lot of academic peer-reviewed journals that help me understand this issue of water equity in the Yucatan. That's all I got for you guys. Thank you.